I'm John Rogers. I'm a professor in material science and engineering here at University of Illinois, and we're interested in electronic materials and electronic devices. Well, if you look out at what exists today in the commercial world, it's lots of very sophisticated classes of integrated circuits, semiconductor devices of various types. The performance has increased over time, but the other thing that sort of characterizes commercial devices is that they're designed to be robust and reliable and time invariant in their properties. But would there be opportunities for a completely different type of electronics, one that is transient physically in its behavior, that is, key components or the entire devices would disappear over time? And so we launched some research efforts around identifying materials and device designs, layouts, packaging schemes that would yield circuits that have high performance in an electrical sense, but offer this additional feature that they disappear over time in a programmed or controlled fashion at prescribed rates, at triggered times, to enable new modes of using electronics in areas where conventional devices would be unsuitable. As of now, we envision three potential modes of use that could be important. The first one is probably the easiest one to understand, is in the context of implantable devices. So imagine in a post-surgical situation, you'd like to put into the body a device that monitors the healing process or performs a therapeutic function to accelerate that healing process. In that kind of scenario, you wouldn't necessarily like the device to hang around after the healing is completed. And so in that type of context, the ideal construct would involve a piece of electronics, sensors, maybe wireless communication capability, actuators, in a format that goes in the body, provides a function for a prescribed amount of time, but then is completely resorbed and disappears in the body after that useful functional period has elapsed. Another one is in environmental monitors. So in addition to transients in the body, you could imagine transients in the environment. So imagine if you have a chemical spill and you would like to monitor the evolution of that spill with large numbers of sensors that are deployed remotely in the field that have an ability to wirelessly communicate some kind of important information related to that spill. Now in that case, once the spill is contained or the remediation process is completed, you might not necessarily want those sensors to remain in the environment. The third one is in the realm of consumer electronics. So as I mentioned before, commercial devices are designed to last forever, have absolutely robust properties. In a lot of cases that's great, but if you look at smartphones, for example, that's a class of electronics technology whose useful lifetime is maybe only 2-3 years. People like to update their phones, for example. And so it's a consequence of that rapid evolution in technology that modern societies are now becoming absolutely overwhelmed by waste streams associated with discarded electronics. And so in that case, you might want key components of a device or the overall system to survive for a period of some years, instead of, say, weeks in the case of an implantable device, but survive for some years and then have an ability to just resorb into the environment after that period. The materials in particular that we found to be most useful involve silk, a purified form of silk derived from silkworm cocoons, as a substrate material, so it's almost like a thin film plastic type of material. It's a great platform for building electronics. We found that for conductors, magnesium is a great metal. If you immerse magnesium in water, it will react with water and dissolve at a molecular level into a benign form, magnesium hydroxide. As a semiconductor, we use very, very thin sheets of silicon. It will dissolve in water to form salicylic acid, which is naturally occurring in the environment and in the body. And then for insulators, we use either magnesium oxide or silicon dioxide. So if you take those materials, the conductors, the dielectrics, the semiconductors, and the substrates, and you put them together, you can manufacture with them. You can make very high quality transistors, integrated circuits, sensors, photodetectors, solar cells, all of the key building blocks that we think form a foundation for a really diverse range of function in this kind of transient technology.